All right, let's do some math. All right, so today we're looking at a complex number question. This is actually just solving a polynomial. It's degree 4. It's called a quartic. And what it's saying is, what values of x could I put inside this x box to make it balance, right? So it's just an equation that you're trying to solve for. Some things that I know are that if it's degree 4, there's 4 answers. And then if I look at the right-hand side here, the scary thing is there's an I, which means that this here is not a real number, okay? It's actually considered a complex number, and it's in the form a plus bi. This is called Cartesian form. The a is the real part. It's just like any real number. And then it has this extra complexity to it. So the b value here is the complex part, or sometimes called the imaginary part. And the I is a number that we make up because we need to figure out what the square root of -1 is, okay? In order to solve this, I can't really use high school techniques. What I'm going to do is I'm going to use a well-known technique to solve this, known as Demoivre's theorem. So what Demoivre said was, take your complex number and rewrite it in a different form. And this is called polar form. So I can take any complex number and take it from Cartesian form. This is Cartesian form. And I can write it as r cis theta. What it means is r is simply the distance that the complex number is from the origin when we graph it, which we'll do. And then inside here, this is just short for cosine theta plus I sine theta. I'm going to turn this into polar form. So what I'm going to first do is I'm going to graph this particular complex number. This is the real axis here. And then this is not the y-axis like a lot of people think. This is the complex axis. So what we do is to graph it, we place 8 right here. And then I'm going to go up 8√3 on the vertical. The vertical in this case is the complex axis. So I'm going to place it about here. So this point here represents the complex number. And I'm going to think about my trig, my high school trig here, where theta was this angle of rotation, and the distance the number was, the point was from the origin, was known as r. We called it the radius. So this distance here is 8, and this distance here is 8√3. And in order to write this in polar form, I have to figure out what r is, and I have to figure out what theta is. I need those two values. R is pretty easy. I mean, that looks a lot like our special triangle, the 1, 2, √3, your 90-degree special triangle, where this here is pi over 3, and this here is pi over 6. Now, if you look here, there's a √3, but it's got an 8 in front of it, and that's got an 8. So if this just looks like it's been scaled up, a version of this. So that means if this is 8 and that's 8√3, the r value here has to be 16. So this distance here has to be 16. You could also use the Pythagorean theorem to do that. And I know that the angle opposite √3 is pi over 3. So that means theta is pi over 3. So in other words, this particular complex number can be written in polar form as 16 cis pi over 3. Now you might wonder, why on earth are we doing that? Well, there's a good answer for it. We can do some equating. So we can equate coefficients, we can equate arguments if everything is in polar form. I'm not saying you can't do it in Cartesian form, but it's a whole lot more difficult. I'm also going to rewrite this in r cis form. So all I do is I just take the x and I let it be r cis theta, because the answer has to have an argument, theta, and it has to have a modulus. R is known as the modulus when it comes to complex numbers. Modulus, and theta is the argument. I don't think that's how you spell argument, but it doesn't matter. Are you with me so far? Okay, so this boils down to, I'm going to do a substitution on the x. I'm going to place r cis inside it. So I'm going to get r cis theta to the 4, and that's equal to the right-hand side, which was turned into this, 16 cis pi by 3, pi over 3. Now, if that's degree 4, you know from math, high school math, that could be written as r to the 4 times cis to the 4. Now, this is where we use Demoivre. Demoivre tells us that when you have a power on cis, you can write it as a coefficient on the theta. So watch how I write this. Times cis 4 theta. The other side is 16 cis pi over 3. We can equate the coefficients, and we can equate the arguments. Mirror, mirror on the wall equals never lies. So this side has to be equal to the other side because the forms are equivalent. So that means that r to the 4 is equal to 16. So r never can be negative. It's always going to be greater than 0, is equal to 2. 2 to the 4 is 16. This also tells us that 4 theta is equal to pi over 3. Okay, well, if 4 theta is equal to pi over 3, I can divide both sides by 4. And that tells me that theta is equal to pi over 12. That, I have one answer already, look. So one of my answers, I know that there are 4 of them. Degree 4 means 4. One of the answers is, if I rewrite it in our cis form, polar form, it's going to be 2 cis pi over 12. Now I'm going to take you back to high school trig. Remember in high school trig, if you had a horizontal stretch here, and of course every sinusoidal pattern has a period, right? The period for which it needs to complete itself. One full period, if you've forgotten, is 2 pi. In radians, 360 degrees in degrees. What I do is I divide by this. That was your b. If you remember the formula for finding the period, I divide by 4. So the period in this case is equal to, I'll just reduce it to pi over 2. Why am I using that? I use that to generate the other 3 answers. So the second one that I'm going to get, this value 2, the modulus never changes. We just add multiples of the period to the argument. Now that's at a 12, so I'm going to write that as 6 pi over 12. And so the next one is also 2 times cis, well, pi over 12 plus 6 pi over 12, which is 7 pi over 12. And the third one is going to be 2 cis. Again, we pick up where we left off. 7 plus 6 is 13, 13 pi over 12. And don't forget the final one, the fourth and final. There are 4, it's degree 4. Tells us that it's 2 cis. Again, 13 plus 6 is 19, so 19 pi over 12. So those are the 4 answers. They're in polar form, and sometimes your teacher may ask you, if you're taking this in university right now, probably, or you're in higher level math and IB, to rewrite these in Cartesian form, which is this form originally. What I want you to know, though, is that when you have 4 answers, the really cool thing is there's geometric interpretations of this. If you were to put these answers on a grid pattern, where there's the real axis and there's the complex axis, this is called an Argand diagram, When you put these on, well, you know, pi over 12 would be somewhere maybe about here, and it would be 2 units away from the origin. Now, since I know there are 4 answers, I have another one fully across. You just drag that across like that. This is also 2 units away. And I know that these are separated by 90 degrees. Pi over 2 is 90 degrees. So if I form a 90-degree angle here and take it right down like that, if I connect these numbers, I end up getting myself a square, which is very, very cool. So when you have degree 4 with complex roots, then you end up constructing a square. So this here represents the first answer, okay? Where there's pi over 12, there's your rotation. This one is the second answer. This is the third, and this is the fourth. So there you have it. That's how we generate the solutions to a quartic when we have complex numbers. Now let's talk a little bit about taking these into the original form, Cartesian form. Okay, so let's take these back to the original Cartesian form. So the first answer that we got was r. I'm going to take cis and write it as what it actually is. So it's going to be cosine theta plus I sine theta. And that's what cis means. C for cosine, I for the imaginary number I, S for sine. So the first one, again, is 2. The modulus is 2, the distance from the origin, times the cosine of pi over 12 plus I sine pi over 12. And all you have to do is plug these numbers into the calculator. So 2 times the cosine of pi over 12 plus, and then the sine of pi over 12 I. And then I could also bring the 2 through if I wanted. We'll do one more just so you get the feel of this. The second one is 2 cosine, this time it's 7 pi over 12, 7 pi over 12, plus I times the sine of 7 pi over 12, and we're doing this in radians. You plug cosine 7 pi over 12 into your calculator. I get negative 0.2588, positive 0.9659, and I don't want to lose the I there, okay? Then you bring the 2 through. So this becomes one of my answers, and this one also becomes one of my answers. There's 2 more that could be written. These are in Cartesian form. Those are written in polar form. All right, so there you go. Solving a quartic, degree 4, 4 answers, where you have a complex number using Demoivre's theorem, using R-cis, and taking Cartesian form into R-cis theta form. A lot today. Slap a like on the video if you enjoyed this kind of content. Leave a comment down below. The comments are now open, and I'll see you right back here in the next video.